Okay, Earth and Space Science. This is the Unit 4 review. The minerals, crystals, and fractures, and information on how they all came together. Okay, now talking about ways to identify different minerals. First we talked about color. When we separated the rocks to start off with, or the different mineral types, a lot of you started separating by color. But we quickly learned that some minerals can have up to 6 or 7 different color phases for that one type of mineral, so that's not always the best way to identify them. Odor can be another one, but there's not really a lot of them that react. The one that will come to mind is going to be sulfur, that had that rotten egg smell. A better way will be luster. Is it shiny or dull? So it's one or the other usually. Cleavage. Remember, this is the way the mineral will split, or will it shatter when it's hammered. So different ones have different types of cleavage. The streak, this is what happens when you basically draw the mineral across to leave a mark. Solubility in water, does it dissolve or do different things in water. The other one will be, does it dissolve or react in water, or additionally, will it dissolve or react in acid? The big one to remember with acid was limestone, and we had a couple questions talking about if buildings were exposed to acid rain, what would happen? The answer, they would dissolve. So that's another key way to remember stuff in different ways to identify different minerals on the upcoming test. Okay, continuing on. Other key ways to identify different minerals. There's going to be optical refraction. Does it have a double refraction? We didn't really talk about this too much, but this is one of the other ways you can identify a mineral. Magnet or magnetic. Basically, does the element stick to a magnet or not? One of the ones that you'll always be checking for is, does it have any iron in it? That'll be a key giveaway. Heavy. This was the experiment we did with this specific gravity. And then the other one that we're learning about towards the end of the unit is going to be the crystal shape. What do the crystals look like under magnification? The other thing too is it like granite, where the crystals are really small and mixed in with other minerals, versus something like obsidian, which is a volcanic rock, and basically they're really big and it was hot and cooled really quickly. So crystal shape is going to be a big one, and that'll also help you identify the different types of fracture. Okay, one of the other things that we can use to identify different type of minerals is going to be the hardness. Scientists use the Mohs scale of hardness to measure minerals and how they withstand applied pressure. This is going to be the scale with 10 being diamond all the way up on top, or if you flip it, it'll be on bottom, and soft will be 1. Examples include talc, which will basically be like chalk. It'll just disintegrate, not very hard. Diamond is the hardest known substance to man. One of the key differences we talked about was the difference between graphite and diamonds. Both composed of carbon, that one element C, but because diamonds have been applied or forced to withstand a lot of pressure, they are very hard. So the difference between graphite and diamond is just how much pressure was applied during their formation. This can be used to basically tell one mineral versus another, and how strong they are, or how hard they are. Okay, splitting open. Remember we talked about cleavage is the tendency of a mineral to break along flat lines of weak chemical bonds. As we moved on with the chapter, or sorry, unit, we talked about how the different crystal shapes will lead to different fractures. Basically, when we were drawing the elements and basically the particle diagrams, remember they will split along the lines where there's the weakest bond. Okay, so we talked about stickiness or strongness. So basically, if there's a lot of bonds, it's not going to split along that line. If there's only a few bonds, especially when we showed the models up front of the class, it's going to split along those lines. So different elements, or sorry, minerals will have different split lines. Look at the picture and you can start to get an idea. Okay, fracture lines. Depending on the mineral's characteristics, it will split or fracture on different ways. Remember, fracture sometimes can be irregular shapes. Perfect cleavage, this is going to be nice shapes. So that's going to be the difference between like looking like shattered glass or always breaking up into different things that look like cubes or different angled pieces, as we learned with some of the crystal activities towards the end of the unit. Okay, we talked about crystals, and crystals are solid materials which solidify or harden into geometrical patterns. A crystal is best described as a pattern of naturally occurring, repeating patterns. Some crystals can form in watery solutions. Examples might include halite or calcite, which can form in cave-like situations in which there's water and there's going to be some form of solidification. An example would be the one lab where you had the little dishes with water solution and you looked at them the following day as the geometrical pattern solidified. Okay, crystallization can occur in watery solutions, and this typically will not be at the highest temperatures, but it will also occur in different pressure situations. An example of a watery solution would be halite. Okay, crystallization can also occur in very high temperature environments. The biggest example would be a volcanic eruption. An example of a mineral forming in this case would be obsidian. The minerals in this case will be very large in size because they have not been given enough time to cool and become smaller, more defined. Okay, examples of mineral and cooling temperatures. Obsidian, as I just mentioned, cools quickly at a high heat, and basically the crystals are very big because they are not given enough time to cool down, and they do not get time to form smaller crystals. Granite, on the other hand, cools very slowly at a low heat level, and basically the quartz minerals have to go into the small nooks and crannies in which they can get into. This basically leads to granite having up to 4 different types of minerals and having different crystal patterns versus something big like obsidian. Okay, remember, temperature versus crystal size. What is the relation between a mineral's solidification rate and its overall crystal size? The higher the temperature and the quicker the cooling is basically going to mean bigger crystal size. Lower temperature and a slower amount of cooling time will mean smaller crystal size. An example in this case will be quartz. Okay, the silicate group. This is the largest group of minerals that exists on our planet. All silicates are made up of the silicate tetrahedron. This is going to include 4 oxygen atoms and 1 silicon atom. So looking at this picture, the red represents the oxygen and the center molecule represents the silicon. You will need to know about the silicate tetrahedron and why it is the most used or found molecule in rocks and minerals on this planet. Okay, ways to identify silicates. If you see silicon, Si, next to oxygen, O, it will be a silicate. Just about all rocks and minerals on Earth contain the silicon tetrahedron. So, for this, the better you know Si and O, the better you'll be able to identify this when you pose with a question asking you to identify a mineral. Okay, silicates divided. Silicates are divided into 2 groups, ferromagnesium and non-ferromagnesium. The root ferro translates as iron in Latin. This is why we have Fe as a chemical symbol for iron. So looking at this, the ones on top, black, are going to be very metallic. Those are going to be examples of ferromagnetism. The one on the bottom, where it's light, is going to be an example of a non-ferromagnesium mineral. Okay, carbonates. The next group you're really going to need to know about is calcium carbonates. These will always have CO3, with C representing carbon next to oxygen, or 3 molecules of this, which will be O3. Examples include calcite, limestone, and dolomite. Remember, limestone will react with acid. Okay, sulfates. Sulfate minerals contain sulfur, S, and oxygen, O, combined with other elements. So SO4 will always be a sulfate. Now remember, sulfur, the chemical symbol is S. Silicon is going to be Si, so please do not confuse these. Common sulfate minerals include gypsum, CaSO4, and barite, BaSO4.